After we learned the standard and normal distribution, now we're going to learn the real applications of normal distributions. Real applications of normal distributions. That means it's not a standard anymore. Okay. But it's still bell shape and symmetric. If you quick review. Okay. So this is a standard normal distribution. We put a z here. So that is a first one is bell shaped and it's a symmetric. Okay. And the second one we have the mu 0, and the third one we have a sigma is 1. This is the standard normal distribution. But for any other or we should call that non-standard normal distribution, it also have a bell-shaped curve. Okay, again, and so that's x, and here's a mu, and this is mu plus standard deviation. So that's one standard deviation above the mean. Here's one standard deviation below the mean. All right, so this is other normal. This is still normal probability distribution. So that's what we're going to learn right now. And I want to tell you that I always ask you to do this. Okay, every time when we deal with the normal distribution, I always ask you just draw one curve and put a 0 and put a z here. At the same time, I share this number line, but I use a different label because I can also use this number line for my x, other random variable, other continuous random variable, not a z, but the other x. And I know mean and the standard deviation. Because for z, that standard deviation is 1 here, right? The mean is 0, standard deviation 1. But for any other, also normal distribution, they also have the bell shape, symmetric. It has the middle part is the mu, which is the population mean. And I just like to label my standard deviation at the end. Usually you're given the values, so just write down the number there. All right, now another thing is very, very important formula. It's a conversion formula, and for z-score for any x value, you're going to use that minus mean divided by the standard deviation. Okay, this used to be very useful, right? This is we're going to use this. Why we want to do this? We have any normal distribution with a mean with its standard deviation, and then we figure out the z-score. We kind of like match that. Why? Because we have a table. We have the table, we can find the probability. Make sense? So that's why we standardize that. Okay. Think about if you have a population which is a bell-shaped or normally distributed with a mean 100 with a standard deviation 10. So 100 here is 110, which is one standard deviation above it. And here will be 1 because it's one standard deviation. So they should have exactly the same shape. And then also you can find the probability. Make sense? I guess not yet. Okay, we're gonna use examples to demonstrate it. It's very, very straightforward. It's very easy, really nice. Now, here's the example. Okay. Heights of a man are normally distributed. Good. I like to see the keyword normally distributed. Height, okay? Distributed. When I do the work, I always write down the keyword for me, so later I don't need to go back to read the question again and again. All right, heights of a man are normally distributed with a mean of 68.6 inches. So that is mu equals 68.6 inches. And the standard deviation, sigma, is 2.8 inch. See, what I'm doing is translating. I'm translating from English to math. Now, what they ask for, find the probability of a man who are taller than a shower head that is 72 inches. So we're looking for what is the probability that here, be careful, this is x. It's not a standard. So standard is a z, and we're looking for x greater than 72. What is this probability? Okay, heights of a man, normally distributed, very good. We have a normally distributed with a mean and standard deviation given. And we ask for what is the probability of a randomly selected person or selected man whose height is greater than 72? Or what percentage of men who are taller than this 72? Okay, so now I keep this here and I'm going to draw the curve. Again, the good thing is you only need to draw one curve. Here's 0. Always do this, okay? Always do this first because it's normal. We're going to use the table, so always do z first. Then do x later. Okay, I want you to follow my step. Mu is 68.6. Put the mean under 0, mu, okay? And put the standard deviation 2.8 in the parentheses after x. It just keep a good note so you see what you're doing. All right, now next one, I'm asking you, what is the x, probability that x is greater than 72? Here is x, right? We keep using it. We recycle this line, or we use this again and again. So now, if you don't look at this 0 and the z, you just treat that as x. Where should be 72? 72, compare that with the 68.6. 72 is to the right. So somewhere got to be here, 72. I don't really care about whether you draw the point here or here. It doesn't matter as long as you show me it's to the right of it, 72. What they're looking for, they're looking for what is the probability that x is greater than 72. So they are asking for this area. Okay? Now, did you see something missing? Which is right here. We have to convert, or we have to standardize this distribution. In another word, we need to find the z-score for 72. Z-score for 72. Remember the formula, z-score for an x, which is x minus mean divided by standard deviation. So z-score for 72, we're going to use the 72 minus the 68.6 divided by standard deviation. Did you see the benefit that I do have that right here, so I don't have to go back to look at my question again and again. Okay, so I got divided by 2.8. Okay, now it's the calculator time. If you pull out your calculator, you're gonna find your z-score is 1.21. Again, just keep 2 decimal places. So 1.21, which is equivalent, 1.21 in standard normal distribution is equivalent to your 72 in your normal distribution. Make sense? Because I'm just using this line to show the same thing. All right, now equivalent thing. Now I'm looking for the probability that x is greater than 72. That should be the same as z greater than 1.21. Okay, do you know how to do that? Z greater than or equal to 1.21, and our table, the table we're using is to the left, so you can either find the z 1.21, find this white area by looking at the positive z table, and then subtract that from 1, or you just simply look at what is the probability that the z-score is less than negative 1.21. So negative 1.21. So it's a 1131. So the answer is 0.1131. 1131. 1131. Okay, so 1.21. Yes. Okay, so that's my answer. All right. The book give different answer, but don't look at that. Okay, so this is one is right. It's 1.1131. That's right. One. Let me double check. 1131. Yeah, that's the right answer. Okay. I think the book give like a 0.1123, and don't look at that. Okay. Okay. So that is now let's think about this question again. I give you a normal distribution, but it's not standardized. It has its mean, it has its standard deviation, and I'm looking for something about the probability over there. I don't have the table for it, so I gotta standardize everything. Then to find the z-score for the certain number, and then so I can get the answer. So this one, there are 11.31. It's like a slightly more than 10%, right? So 11.3% of the men who are taller than the shower head. Okay, that's this example. Okay, let me ask you another example. Let's work on another example. I think right now you already get the idea, like how do we use that, okay? So another example. When designing equipment, one common criteria is to use a design that accommodates at least 95% of the population. What do you think about the shower head? The shower head height is 72, and it accommodate how many? Because there is 11.31% of the people of the men higher than that. So for men, there are 89, about 88 point some percent of the men who are whose height is lower than the shower head, but including women. So that sounds like a very good thing. Okay. So now when we talk about the door, okay, we want to look at the height of the door, and that would allow 95% of adults to walk through the doorway without bending or hitting their heads. Okay, let me give you something. The heights of adults are normally distributed. I like this. Normally distributed. I think every time when you hear normally distributed, you should be very excited, okay? Because there's something that we know how to do it. Okay, normally distributed with a mean mu equals 6.2, and a standard deviation 3.8. Okay, mean standard deviation. Now, how does the result compare to the door height of 80? Right now we have 80 inches. That's a door, right? Okay, 80. So, do you think this 80 inches, this standard, or this door height 80 required by the International Residential Code, do you think that 80 can accommodate 95% of the adult? Let's find out. Okay, how should we do that? Again, draw the curve and put here's a 0, here's a z, and here is a x, and we put the mean 6.2, and we put the standard deviation 3.8 here. What we're looking for? We're looking for what is the probability that x less than 80. I want to see whether this percentage or this probability is this compare that with a 95%. We're going to see how it works. So here's a 66.2. We talk about x, and where should be 80? 80 should be somewhere here, right? So that's 80. Did you notice that you have to find the z-score here? Once you put it that this way, you're going to find that. So the z-score for 80 is x minus mu over sigma. So that will be 80 minus 66.2 divided by 3.8. Okay, so you're going to use your little calculator. You're going to get what? Let me see my calculator here. Okay, so I have a 80 minus 66.2 and then divided by 3.8. I have a 3.63. I get this. This is my z-score here, 3.63. And I'm looking for what is the probability to the left of this one. And the interesting thing is, if we're looking for this probability, we can find this little tail by, either by positive 3.63 or to the left, so that's easy. 3.63, 3.60123, 9999. So the probability that x less than 80 will be the same as z-score less than 3.63. That's 0.9999. So 99.99% of the adults, their height is less than 80. So then this 80 inches is perfect. That's not a problem at all. So that's one way to solve it. Okay, that's one way to see. There's another way to do it. Another way is to find what is the critical value. Critical value is this. We are looking for, again, here's a 0 and here's a z, here's x. We put the mean here, 66.2, and I put here standard deviation 3.8. Okay, I want to have the door height that can accommodate 95% of the adult, which is some number here and all the way to the left, 95%, or 0.95 or 95%, which is the same thing. Okay, so I'm looking for, if you are the one to make this industrial, the residential code, what would be the height requirement you put there for the height for the door? And then you want to accommodate 95% of the people. So let's see, if we have 0.95, can we find the z-score here? Yes, it's called a z 0.05. Let's see if you remember that. Here's 95%. So to the right is 0.05, which is 5%. Okay, so if the area is 0.5, 0.05, here, let's see, 0.05, which is another table. Do you remember this number? .645, right? So here is 1.645 because this little area is 0.05. And if you forget about this, go to my previous video. All right, now what would this be? Do you remember the formula that z equals x minus mu over sigma? Do we know z? We do. 1.645. We're looking for x. We just leave that. We just put that as x. Minus mean, 66.2, divided by standard deviation. Can you solve this for x? You multiply by 3.8 both sides, and then you add 6.66.2 both sides. So x will be 1.645 times 3.8. Then you're going to plus 66.2. If you use your calculator, you are going to get a 72.451. Wow, this is much lower than 80, right? Because if you just put a 72.5 inches, that can accommodate 95% of the adults. So 80, that's good enough. That's what we know, isn't it? All right. Okay, so I think we're good. on this. I believe you get the idea. You know the standard and normal distribution, and then you know how to deal with any normal distribution, which is the key here, right? Standardize it. And then you're going to draw a graph and then make sure that you put two lines here. One line number for z, one is for x. I wish you put all those numbers there in your graph, okay? Because some people are lazy, just randomly put a number here and then without putting things there. Eventually, they're going to get confused. And if you do it this way, then you're going to be super clear to see, oh, this is what we're looking for, okay?